And this is my plan for today. Well, first of all, as I said, the tutorials will be quite integrated with the lectures because a lot of what we do in this course is really examples anyway. But nonetheless, we'll put more emphasis on examples in tutorials and try to introduce, or not to introduce, really new concepts. With that in mind, what I'd like to do today is to just try to give you guys a little more insight into capacitors and inductors and what they do, how they behave in circuits, picking up from where we left things in the lecture yesterday. And once we play around with these enough today, then tomorrow in the lecture we'll be in a good position to formalize the concepts around capacitors and inductors, take a more systematic look at them. That's one of my goals. And the other one is to look at an example, or depending on time, maybe two, of just solving circuits, okay, using concepts that we have seen. So let's go back to this problem that we saw yesterday, where we had an inductor with inductance L. And yesterday, we first looked at an example where we had a voltage source connected directly across this inductor. And then we saw there was some trouble with that if you had a constant voltage. And then we looked at another problem that had a current source connected to it. And then there was also a resistor in the circuit. Now I want to not have the resistor first. At first, just look at this. There I have simply a current source. Let's call it IS, like we had yesterday, connected to that inductor. And IS, so again, this is all examples. And IS has this behavior, what we had yesterday. So it's 0 for a very, very, very long time, in principle, since minus infinity on the time axis. And at time 0, it jumps suddenly. In no time, it jumps to the value I0. So this is the temporal behavior of the current IS, given by that source. Okay? I want to see what happens in this circuit and what the inductor does. So like always, let's start giving names to things that we'll be talking about. So this is V, and this is I, the voltage and current of the inductor. And I've chosen to use the polarities the way I've shown. Now, you might already recognize very quickly that by applying a simple KCL, you will see that I sub s is equal to I in this circuit. So perhaps I didn't need to explicitly indicate an I there, but nonetheless, I wanted to start simple and not to have to see one step ahead of time. So now let's see what happens in this circuit. What is the behavior of V and I? Well, I is the same as IS, but what's the behavior of the voltage across the inductor in this problem? Okay. Well, how do I solve this problem? No different from anything else we've been talking about so far, KVL, KCL, element relationships. So can you guys take a minute to do it on your own? So the question is, what is V of t? For all time. So I'll just, especially when you encounter a problem where you don't know where to start where you can't go wrong. KVL, KCL, element relationships. Okay, write them down, and then see what you can do with them. First of all, if I want to, well, what are the nodes here? I have this node and this node. So I have two nodes. So I'll have one KCL, like we saw before. And I simply have one loop. So one KVL. And I have two elements. One of them has been defined by its current, so its element relationship is already sketched out up there. The other one is an inductor, V equals LdI by dt. So let me write those down. First of all, to write the KVL, I need to have indicated all the voltages. Now, what's the voltage across the current source? Yeah, so in general, a current source can have any voltage, an ideal current source, right? And in this case, it's a simple KVL that will tell us it's the same as that V. So, but I want to give it a name first. So let's say this is V sub S, okay? So my KVL will be minus V sub S plus V equals 0, okay? And my KCL will be at the top node, let's say. Oh, interesting. I have to be careful today because it looks like the corner of the screen here is cut, or the edge. So let me know if you can't see what I'm doing here, okay, if it goes too much to the side. So the KCL at the top node is simply IS going in, I leaving. So IS minus I equals 0. And then the element relationship, IS we already know, so that's one. We know IS, so that's for the source as a function of time. And then the other one is V equals LdI by dt. Okay. So let me see what I can get from these equations. Well, first of all, from this, I can see immediately that V sub S is the same as V. Many of you said that intuitively just by looking at it, but that's really the manifestation of KVL here. So V sub S is V, is one simplification. And the other one is that the current I is the same as IS. Okay? And that is true at all times. KCL is true at all times. Okay? Now look at what we have. I is equal to IS, and we know IS for all times. So from here, we know I, in fact, for all times. It's the same as IS up there, sketched like that. And if I'm interested in V, all I have to deal with is a simple relationship down here, V equals LdI by dt. So all I have to do is to take the derivative of that function that has been drawn up there. Okay? Now that's a function that has been defined in time. Let's take its derivative. Well, you will see immediately that there are the function has different behaviors in different ranges of time. So let's recognize that for t less than 0, well, the current is constant, is a constant 0. What is its derivative? So V of t is 0. And we see the same thing for t greater than 0. The current is I naught, but it's a constant, so its derivative will be 0. So for t greater than 0, Vt is also 0. How about at t equals 0? How about at t equals 0? Yeah, you have a function that's not continuous. There's a big jump. And so the derivative at that point is the slope of that vertical jump. So So this is the answer to this problem. You see, I have done nothing but applying KVL and KCL systematically. Now, I think both the KVL and KCL were almost trivial to most of you. Because as soon as I started saying things, they said, oh, you said, oh, V is the same for the current source, and that current I is the same as IS. But there's something about maybe seeing a new problem that's maybe intimidating, and one tries to guess the answer somehow before one actually does it systematically. Because if you do it systematically, this is not a difficult problem. So I'm trying to use this mostly to understand inductors, but also as an example of not trying to know the answer to the problem before you solve it. Just taking your time and going through it step by step. Okay. Now, well, OK, so this infinity here is problematic. So the question is, yesterday I said that after 0, we had a transient. It didn't go immediately to 0, right? We were solving a different problem yesterday. Yes, and what I want, it's actually a very good question, because this shows you how a small change in a circuit could lead to a very dramatic behavior. And so in general, you cannot take the solution from one circuit and apply it to another, even though they might look very similar or have a lot in common, which these two obviously do, right? And that's why I emphasize solving every problem from the beginning. Now, once you solve enough of these, you will be able to recognize patterns of what does repeat and what does transfer. But this is a fundamentally different problem. And you see, yesterday, I did not make an assumption that there is a transient. We solved the problem. We came up with a differential equation that led to an answer that had a transient form, right? So I didn't know anything beforehand. Yes, so the question is, what if yesterday we just solved for what happens after a very, very long time? Well, if you had been asked what happens after a very long time, that would be the answer, right? But if the question is asking V of t, question mark, right, at all t, then obviously you can't skip a big chunk of t. So how do I deal with this infinity? It's problematic, a pretty innocent-looking circuit. So let's say the current in the current source goes from 0 to 1 amp. And it requires infinite voltage. That's not good. So this should tell you that you should not do this in the lab, right? If you have an inductor and you feed it a current and or connect it to a current source and turn it on, something bad will happen. Because that sudden change in the current of the inductor requires momentarily, but nonetheless, an infinite voltage across it. That's not good for the inductor. That's not good for the current source. And it's not good for the operator there, right? Now, typically what happens if you're lucky, let's say a wire breaks or the current source breaks down without a hazard. But that can't be guaranteed. So you should never do this. But if you actually forced things, so if you did this on paper, like we did here, you would really require an infinite voltage at that moment. So your voltage is basically a delta function. So if I were to plot V of t, is 0 here all the way, and 0 here all the way, basically all the way to that time 0 minus and all the way to that time 0 plus on this side. And then at that point, it's a delta function. OK? Delta function has a value of infinity at that specific point. OK. Now, what is the height of this delta function? So what is the height of the delta function in general? Well, it's infinity, but do we have to say something about it? Any suggestions? Let me ask you another question. So you guys have seen the delta function in math? No? So, OK, so the delta function is this. So exactly this, a function that has a value of 0 all over the place, except at point 0, where it has a value of infinity. OK? So let me ask you, it would have helped if you had seen the delta function in another context, but so we'll skip that. Here's something very interesting and important that you can do. Tell me what the integral of the function v is from minus infinity to infinity. So we have the function v. Can you work on this? It's a good start. How about it's 1 multiplied by something? A delta function, typically the way you define it is its integral is 1. But this is a scaled version of a delta function. Take the integral, by the way. You don't need to guess. Take the integral. You have the function v. Take the integral. So maybe I can write this, because my function is defined like that, 3 different segments. Maybe it's easier to do it once from minus infinity to 0 minus, and then between 0 minus and 0 plus. And then between 0 plus and plus infinity. Now, what is the integral of v dt from minus infinity to 0 minus, just before the vertical axis? It's a constant, which happens to be 0, because it's the area under that curve, right? So that's 0. And the same thing for the other side. So it's really 0 there and 0 on the other side, but you have what's left in the middle. OK? So all we have to do is to evaluate the integral as we go from just to the left of the vertical axis to just to the right of the vertical axis. And to do that, well, now you might say it's a function with a height of infinity. We don't know how to deal with it. So let's see if there is something else in the problem that can help us. And again, as very often is the case, there aren't too many things in the problem. So just go around and look what might help. If you look at the inductor relationship, if you do a little bit of rearrangement, v dt is just L times di. OK, so let's replace that from the inductor relationship. Okay, and L is just a constant, so it comes out of the integration. Now, what is the integral of di going from one point to another? It's just the difference in the initial and final values of I, right? It's just so this is the integral of di is I. So this is Li going from 0 minus to 0 plus, or simply L times I of 0 plus minus I of 0 minus, which is L times. Now, what is I of 0 plus? It's that I naught, right? Just after 0, the value of the current is I naught. What's the I of 0 minus? It's 0. So L times I naught minus 0. Okay. Things of this nature happen quite frequently. To deal with the discontinuity over time, to do an integration like this is not uncommon. So I just wanted to show you an example. So what does this tell us? This says to us that, well, first of all, we saw that the inductor does not like this sudden change in the current. And if you forced it to undergo such a change, it would require an infinite voltage. So that's one thing we saw. The other thing we saw was that essentially that infinite voltage, the reason it is required, another way of looking at it, is that over no time at all, going from 0 minus to 0 plus, the integral of that voltage has to be a finite value. And that's why that voltage has to be infinity. Because there is no width of time over which this current is ramping up. It's sudden, and that's why you need an infinite voltage. Okay. So again, don't do this in the lab, okay? Now let's go from here. Anything you guys? Yes. So the question is whether I pulled a trick here. In other words, if I had done it another way, I would get infinity, right? And the answer is no, because what we are, this is maybe one way to look at it. Now this is, what I'm going to show you is not a completely accurate picture, but it will help with the insight. The delta function, in fact, this is how you can think about it. Let's say I zoom in on the axis. Now, a real delta function, no matter how much I zoom in, it's 0 all the way on both sides. But imagine that you have something that's not a delta function, but it's something like this. Let's say this is 1 attosecond. Does anyone know how much an attosecond is? So there's minus 1 attosecond. How about femtosecond? Does anyone know? Picosecond? Nanosecond? OK, so what is atto then? Count back. 18, minus 18. OK, minus 18 seconds. In fact, it's not a bad number for this example, because electronic processes typically happen on the scales of tens to hundreds of attoseconds, the really fast processes. So here I have set really a very, very short time. Now imagine you have a function like this, OK, that has a very tall peak, but it's confined to a very, very small region. Now that peak is very tall, but it's not infinity, OK? Now, I think you would be OK with me saying the integral of this is something finite. It has a very small width. It has a very tall maximum, a large maximum. but a very, very small width, right? So this integral is finite. That area is finite. Now, the way to think about the delta function is to squeeze this further and further. Bring the two points closer and closer and closer ad infinitum to the axis. And to make up for that, make the height higher and higher and higher while maintaining the integral, while maintaining the area under the curve. Eventually, well, you will never get to infinity, but if you now take the limit, you get infinitely close to the axis on the two sides, the peak has to go infinitely high. And so the integral stays the same. It's the area under that. That's basically a delta function. And what this integral is, what the surface area actually is, for a delta function, you define it as 1. In our case, it's basically a scaled delta function where the area comes out to be Li naught. Okay? And so this is actually pretty useful. If you hadn't seen delta functions elsewhere, this is it's something that happens very, very commonly. Okay. It's a very useful function. So in the limit, I want to say this goes to infinity, and the two sides are minus 0, 0 minus, and 0 plus. Okay? So I don't want to leave it, or yeah, maybe I'll just draw another one next to it. In the limit, now this is 0 and infinitely tall peak. And that's why you have this arrow suggests infinitely tall, and then 0. Okay. So now I want to augment this problem by adding a resistor right next to that inductor. So what we were looking at yesterday. And I want to now come at the same problem from a different angle. So I have the same inductor. I have the same current source. And I also put a resistor R right here. So I want to see how things change now. Okay? And so I want to do it first qualitatively. If I have no resistor there, so if it was disconnected, I just had L, we just saw that the jump in the current IS had to immediately be forced upon the inductor, L. And that was something that the inductor did not like. Or it said, well, if I have to do it, then give me infinite voltage. That's the compromise. And that's what happened. How about now? It was KCL that forced all that current to go through the inductor, but my KCL has changed now. KCL in this case is IS. There is still that I and the same V. But here I have I sub R. So KCL is IS minus I sub R being equal to 0. So KCL does not force IS and I to be the same anymore, because there is that I sub R that can take part of that burden. So qualitatively, what do you expect would happen the moment that transition happens? Let's look at the circuit. The moment that transition happens, in this branch, the current IS is just going from 0 to I naught, an abrupt jump. Based on the KCL at that node, that jump, that the change in the current now has to be distributed over the inductor and the resistor, right? We just saw that if the inductor took any sudden jump in the current, it doesn't have to be IS, even if it was 1/1000th of IS. If it was a sudden jump, a perfectly vertical jump, it required an infinite voltage, right? Can the inductor have an infinite voltage even for a small moment in the circuit? Why not? Can someone tell me why not? I see some heads shaking. So.
Because you can't supply infinite voltage.
Why can it not supply? I mean, an inductor can take the voltage. Yeah. Yes.
Because if the inductor has infinite voltage, then so does the resistor, and there would be infinite current.
Yeah, so there's other constraints in the circuit. You see, if I didn't have the resistor, the inductor would say, OK, I'll take the jump. My voltage will be momentarily infinity. But now, if V is to become infinity even for no time at point 0, then the voltage across the resistor is the same, right, by KVL. So if the resistor has to have infinite voltage, what is the current in the resistor? Infinity, V equals RI. Now, KCL will not allow that, right? Because the current source has a finite amount of current, I naught, in this problem. From which, then, it follows that you can't have an infinite voltage, which means, then, that the inductor cannot take any of the sudden jump. So the entire sudden jump of the current will be taken up by the resistor. So if you look at time going from 0 minus, where everything was 0, to 0 plus, at 0 plus, immediately after that sudden jump, the current in the inductor hasn't changed yet, but the current in the resistor has jumped to I naught. And in the circuit, there is no infinity happening. And this is a circuit that you can build in the lab. There is no problem. Okay. So now I want to see how I can, I just want to write it down mathematically, OK, to be a little more formal. So KCL tells me this, OK, and KVL tells me that Vs and VR there will eventually be the same as V. Okay, minus Vs plus V equals 0, minus V plus VR equals 0. And then I also know that VR is RIR, and V is LdI by dt. So now I know that, well, for t less than 0, Is was equal to 0. And everything was 0 for a very long time. After the jump happens, immediately after the jump, Is is I naught. Okay. If any of this sudden jump were to be taken up by the inductor, as we saw in the previous example just above this, as we just saw, it would require an infinite voltage V at the point t equals 0. But then, given that VR is the same as V, the same as V, these would tell us that IR is simply V over R. If V is infinity, IR would also be infinity. So if we call this equation 1, so then from 1, we would have I infinity at t equals 0. Now, if I is infinity, sorry, IR, we called it IR. Now, let's look at the KCL up there. If IR is infinity, I just said it can't be because IS cannot supply infinity. IS is I naught, right? Is there something else that we could say about this KCL up there, or looking at that KCL? Let me put it this way. Are you guys comfortable for me to say that the KCL tells us, because IS jumps to I naught, that IR cannot be infinity? Are we comfortable with that? OK. So I'll leave it at that for now, but then I'll ask you guys to think a little more about it at home on your own. So the KCL will tell us, because IS is simply bound to I naught, we can't have the infinite current IR. So I'll say this contradicts the KCL since the current IS is not infinity. Okay? So this is just a formalization of what we discussed right now. Like I said, I'll leave it at that for now, but go think about it a little more at home. See if there is something else you would like to dig a little bit into. Now, if you want, the summary of this discussion really is this, that an inductor in a circuit will try to oppose sudden changes in its current. It does not like a sudden change in the current. Under special circumstances, like the first circuit, yeah, sure, if you absolutely force it and there's no other way, it will take it as long as some other KVL or KCL is not violated. But if you give it another way, it will take that other way. And so this is the example we saw in the circuit. The other thing I want to say is, if there is no, if the sudden jump cannot at all be taken by the inductor, so all the sudden jump is taken by the resistor, you know that the current in the resistor immediately after the jump is the full IS. So the result of this is the current in the resistor at time t equals 0, 0 plus, is equal to I naught, which then says the voltage of the resistor at time 0 plus is R times I naught, which then says, well, the voltage of the inductor, which was the same at 0 plus, is R times I naught. This is what we talked about briefly at the end of yesterday's example. And we will do this kind of thing more and more. Okay. There was a question somewhere, I think. Yeah.
So what would actually happen in the lab if we did the first circuit? Because obviously the current source can't supply infinite voltage, right?
Infinite current.
Infinite current, or yeah.
Yes.
But inside the current source, I think you have to have first voltage from the outside.
Yeah. Yeah. So what would happen if we actually did this? Now again, before I get myself in that discussion, I want to remind you, don't do it, okay? But what would happen? If you have a very, very, very well-designed current source, it would have some protection mechanism for this not to, for this not to cause any problem. Now, in reality, you do not have a current source that can change its value of current over 0 time, right? Nothing happens suddenly like that. Things can happen very fast, but not absolutely suddenly. That's one thing. You also typically will have some parasitics, some other leakage paths that will make it so that in reality the inductor is not the only element in the circuit. There is some resistances somewhere. Now those paths might not allow for a lot of current, but they will allow for some. So if you're lucky enough and there is enough leakage and the current source is well designed to protect itself, namely, if it sees that it's trying to change things quickly, but the voltage across it is developing rapidly, so it won't do it. It will have a protection mechanism, a control circuit that will say, I'm not going to change rapidly. Okay? But if it didn't have any of these things, and it tried to change very rapidly, now it's not going to be instantaneously changing, but it's going to be very rapid. So your voltage is not going to be infinity. That slope of that change is not going to be infinity, but it's going to be very, very large. So you will have momentarily a very large voltage drop across the inductor. And that could end up frying something in the current source, could lead to maybe a small arc somewhere in the air. And it could potentially have catastrophic consequences. Fire, it's a hazardous thing. Okay. All right, so I think it's time for our 5-minute break, and then we'll look at another problem after this. Okay, so let's look at a different type of problem now. So this was just an example to see a little bit how an inductor behaved. Now I want to look at a problem with a capacitor. Take this circuit. Same IS of t as before. So it's the same step function, jumping from 0 to I naught. What is V of t? Take a couple of minutes, think about it. And in the same spirit as the question I asked yesterday, is this a good circuit or B, bad circuit? Let's see if I can turn on my eye clicker thing. Mostly a bad circuit, but maybe not a resounding answer to the or confirmation of being a bad circuit. Okay, maybe we can do it together now. So again, I want to solve a circuit. I'll start giving things names. Vs here and I there. My KVL minus Vs plus V equals 0, KCL, Is minus I equals 0. So these are, you might say, trivial, but it took me only 10 seconds to write them, so it's not a big deal. So from here, I conclude that I is the same as Is, which is handy. And the element relationship is that of a capacitor, which is I equals C dV by dt. I think we talked about this last time, last week maybe. Now, if I want the voltage, well, it's the integral of the current. So then from that, dV is 1 over C I dt. And if I want then to find the voltage at a given point in time, I have to integrate from minus infinity to that point. So then V, which is at a given point in time, V of t, which is the integral from the beginning of everything to that point t of dV, is simply 1 over c, the integral but remember that I is the same as Is, so I'll just replace that. Now, if I look at my Is, maybe I should just draw it here to have it handy. Is was 0 everywhere until point t equals 0, and then jump to I naught. This was my Is of t. So if I take the integral, now for any time less than 0, the integral under that curve is 0. Is was 0. There's no area under the curve. So t less than 0, Vt equal 0. T greater than 0, though, you see, as soon as this current Is jumps to this finite value, as you move in time to the right, the area under the curve builds up. So the integral becomes V of t becomes basically the integral, 1 over c, the integral from minus infinity to 0 of Is dt plus starting from 0 to time t. And the first one is simply 0, because for the time less than 0, Is was simply 0. So this is 0. And then the second one will be, so it's 0 plus 1 over c integral of 0 to t. And Is has the value I naught here, which is a constant. So the answer is then I naught over C, the integral from 0 to t of dt, which is I naught over C times. So I just broke up the integral. You see, the integral is supposed to be from minus infinity to t, right? So I broke it up to minus infinity to 0 plus 0 to t. And the reason I did that was because Is had different values in the two intervals. So it's interesting. This circuit does not involve any sudden jump in the voltage or, in the voltage, nor an infinite voltage. So from that point of view, at time 0. So from that point of view, it's quite OK. In fact, if you plot this, you see it's a function that was 0 up until time 0, and then after that it starts to grow linearly. So V of t was, the solution came out like this, 0 there, and then grows linearly with the slope being I naught over C. I've just plotted the answer. So you see, there is no infinity at time 0, but if you give it enough time, it will keep charging up to higher and higher and higher and higher and higher voltages. And that can't be good. Right? It's out of control. So this is, again, a bad circuit from that point of view, in that if you connect a current source to a capacitor just like that, it will keep charging up. Remember, the charge in the capacitor, Q was CV, right? So if V keeps growing, Q is growing. And there is a very interesting analogy here, and simple analogy, with what we talked about maybe 2 weeks ago when we started the discussion on charge and current. This really is like filling up a bucket of water. So you have a hose with a constant flow of water, and you start filling things up, and you forget about it. You keep going. At some point, you're going to have a flood, right? In the case of a capacitor, at some point, there's so much charge buildup, the voltage is so high, the electric field inside the capacitor is so high that it's going to arc. Maybe before that point is reached, the voltage is so high that the current source can't take it. Again, some of those bad things that we talked about before happen. So again, keeps on growing with time. Without a limit, basically. Right? So that's what I want to emphasize. And that's why it's not good. So again, don't do this in the lab, okay? Because if you do it, at some point, one of these things will have a serious problem. How about this? Let's connect a voltage source to the capacitor. So I'll call this again V. This one is Vs. Maybe call this I sub S. And this time, the source voltage is 0 up until time 0, and then it suddenly jumps to the value V naught. Is this good, bad? What happens? Absolutely. So the answer is, it's also something not good here, because of the simple reason that KVL here imposes an equality between V and V sub S. So that voltage source is forcing its voltage across the capacitor. So if there is a sudden jump in the value of the voltage there, the capacitor will have to take it. So you have a sudden jump in V. But for the capacitor, so this means a sudden jump in V requires an infinite current. It's a problem. How could I make this turn this into a good circuit? Put a resistor next to it right in the previous circuit, right? So how about this? Problem fixed. Across the voltage source is jumping suddenly. Well, the same voltage is across the capacitor still. So the existence of this resistor here doesn't help. So what should I do? How about that? Right? Now that sudden change in the voltage can be taken up by this resistor. Okay? In the same way that the sudden change in the current was taken up by the resistor in the previous circuit. So you start seeing patterns of behavior and, in fact, a duality between the way inductors and capacitors work. How about this? Okay. So this one is not good. So how about that? Okay. So I want you guys to go home and play with these a little bit on your own. And like I said, we will talk about these capacitors and capacitive and inductive circuits in more formal ways starting tomorrow. Okay. So I think enough with capacitors and inductors for today. I hope this has helped initiate some ways of thinking and hopefully given you some insight. It's something that really comes with looking at different problems. Okay. So I want to move on now to another problem. And you see the current I up there in that branch at the top? That's my question. What is the current I? And I'd like to ask you guys to try on your own a little bit. What's the current I? So solve this circuit to find current I. It's no different from the kind of things you would see on your homeworks, for instance. So it's just really meant to be a practice problem. Okay, let's take a look at this. So first of all, like I've promised you before, if you write your KVLs and KCLs and element relationships, you will find the solution to this problem. Okay? There is nothing mysterious here, and you don't need any. Does anyone have the answer, by the way? Number for? Yes. Okay. You don't need any additional knowledge. Okay? Now, this looks maybe a little convoluted because I have a couple of wires going over each other. Sometimes you can maybe see things better if you know, a real circuit with wires, the wires, you can pull them around, right? As long as you don't change the connections, the circuit stays the same, right? So it doesn't matter. So you can rearrange things a little bit here. It might make things easy. But indeed, you don't need to do that. You can just write the KVLs and KCLs and element relationships for everything and solve it. But to make things easier on myself, this is what I want to suggest to rearrange a little bit. Look at this. This resistor here is connected on one side all the way here, and on the other side all the way here, going over the other way. Right? So I could just, if it was something I had in the lab, I could just physically move this resistor to the other side. So I could have it here. Now, I shouldn't change the order of definition of my voltages, so it would be like this. It's literally the same circuit, so I'll scratch this off. OK, I have taken it and put it there. Now you don't have that twisted shape anymore. Maybe it's a little easier. So now you start writing your KVLs and KCLs, and here is one of your KVLs. What does this KVL tell you? You have a loop that starts from here and goes there. KVL, so the sum of the voltages in that circuit, in this case minus Vx going in that direction, according to my convention, is 0. There's only one voltage in there. Vx equals 0. So yes, this is a big circuit, but there is a KVL there that is an equation with only one unknown. So that's somewhere very simple to start. If you start with that, you get Vx equals 0 from the KVL. Then let's look at the next KVL right next to it, the one that involves that voltage-dependent voltage source. 5 times Vx. Well, if Vx is 0, 5 times Vx is easy. That's 0. So what does that tell me about the voltage across the 8 ohm resistor? 0. And what does that say then about the current Ix? 0. So then from here, another KVL gives me 5x equals 0. And then another, that tells me 5x equals 0. And then another KVL. So let's call this KVL 1 and this KVL 2. Then KVL 2 will tell me that essentially 8 times Ix is 0. So Ix is 0, and therefore the other source up there, 2Ix, is 0. Now this source up here, the 2Ix, is, again, remember, it's a voltage source. Okay? It depends on a current, so it's a current-controlled voltage source. It's a voltage source, but its value is twice the value of the current Ix. Now, if Ix is 0, well, twice Ix is 0. So that voltage source there has 0 volts between its two ends. Right? What is a voltage source that has 0 volts between the two ends? It's just a wire. Okay? So your circuit has very quickly reduced to something that's sitting on its own, completely doing nothing, 0 volt across the 2 ohm resistor with 0 amp going through it. It's just a piece of wire extra connected there, doing nothing. And then that branch, 5Vx, that has essentially no voltage because of the other thing. And as a result, the current through the resistor, 8 ohm, is also 0. So all of this imposes 0 volt difference across the 8 ohm. So that becomes a short circuit. And similarly, as we just mentioned, 0 volt across the 2Ix voltage source up there. So that's also essentially a piece of wire. So let me now draw the simple version of the circuit. So I had 2 volts up there, and then the 3 ohms, and 7 ohms, and 10 ohms. Three, 7, and 10. And now you want this I. Well, now this is a much simpler circuit to solve. You have 2 KVLs, a KCL. So what I want to point out here is, now you see, I haven't done anything other than really writing KVLs and KCLs. I've just done it very quickly to make a point here. And that's this. That it's always a good idea, maybe before launching into a purely mechanical approach to solving the circuit, to maybe inspect things a little bit. Okay? Take a look around. See if there is something that catches your attention. Now, this can also be a very tricky business because you could end up making a wrong judgment call. And here's the guideline. You should always inspect and try to understand the circuit. Okay? But never guess the answer. So what I've done here is not taking a guess at and simplify things accordingly. I did something very, very rigorous. I did redraw the circuit, if you want, in a way that made it easier on me. And I started applying KVLs and KCLs. It just so happens that one of the KVL equations just had one unknown in it. So I didn't need the other KVL equations before I could solve this one. But you didn't need this. You could have written all the equations, and you might have ended up with, I don't know, 15 equations or whatever. And that would have been just fine, because once you have that system of equations, you start solving them. Again, you should go through and see where is a good point to start. And as you go through that list, you will see that one of those KVL equations is minus Vx equals 0. And that would have been your starting point. Okay? So you don't need to use guesswork. But it is a good idea to try to get some sort of feel for the circuit and the way the connections are before you launch into a full-blown solution. Okay? Now, sometimes there might not be anything that simplifies things, and you might be faced with a tedious problem of having, I don't know, to solve 5, 10 equations. That happens. But sometimes there could be things like this that simplify things.